Multivariate distributions. Now we're going to get real sophisticated, folks. This is going to be fantastic. You're going to love this. Let's say you have two random variables. We'll call them x1 and x2. And these random variables are discrete random variables. They're joint probability mass function. Joint probability mass function. That is there's a function, we call it a probability mass function, but it describes how these two random variables behave together at the same time. Sometimes is expressed like this. Okay, there are a million different ways to denote this. Okay, sometimes we write this. Sometimes we use a little p. Sometimes, if the variables are understood here, we don't even put them in the subscript. This is the meaning of it. Okay, it's the probability that the first random variable takes on this little value, and that the second random variable takes on that little value. That is, and just remember that we're abandoning, sometimes we abandon this intersection symbol there in favor of a comma because it uses a lot less ink. Okay, it's cheaper, better for the government, right? Okay, so that's what that is. Okay, so and we'll do some examples in a minute. Let's also take a look at oh, and by the way, this is for all x1 and x2 in the reals, right? Okay. Let's also take a look at the joint distribution function. The joint distribution function. Sometimes we just say joint distribution function. Sometimes we say joint CDF, which is not short for joint distribution function, but sometimes we just say distribution function when we actually mean cumulative distribution function. Okay? So sometimes we say cumulative, sometimes we don't, okay? But this is what we mean. We actually mean the joint cumulative distribution function, or the joint CDF. I'll probably just write this a lot, because again, it takes a lot less ink, right? And we don't want to waste ink, okay? It looks like this, okay? Again, we'll use big F like we did before, but I'll denote that we're considering two random variables here. And I'll use these little x1 and x2 to sort of represent their placeholder values for these little deterministic counterparts. They look like they're random analogs there. So this is defined to be the probability that x1 is less or equal to little x1 and x2 is less or equal to little x2. Okay, so it's the chance that the first random variable is less or equal to this amount, and that the second random variable is less or equal to that amount. We have some probability axioms for jointly discrete random variables. These mimic and actually follow from the basic probability axioms. Okay, pretty simple. First of all, the chance that x1 takes on the value of little x1 and x2 takes on the value of little x2 has to be non-negative, right? Okay. And also, if I add up all these probabilities, note that each one of these probabilities is the probability of these events in here they're disjoint events, right? That x1 equals little x1 and x2 equals little x2 versus the event that like x1 equals some other number, x2 equals some other number. Those are all disjoint events. So in fact, it should be that the probability of the union is the sum of the probabilities. It turns out if I run through all the possible values of x1 and x2 and sum them up, then I need to get 100%.